Thank you, Jeff. I want to first apologize. I'm going to give the talk sitting down because I strained my back this past week, and while it's feeling much better today, I don't want to stand for an hour. So I hope you forgive me for that. I'll just sit. The second thing I should say is that it's somewhat gauche to schedule one's own talk at a conference one organizes, and I wouldn't have done it, but it's Yakir's party, and he wanted to hear me speak, and so this is for Yakir. If you look at my first slide here, a few things to note. First of all, this is a picture I showed at the 80th birthday, and I'm astonished how much like a baby I look there. It's amazing what can happen in 10 short years. But I think about John and Ephraim, you guys look ageless. That's very impressive. Paul looks a little youthful, even though he's much older than I am. But it's fun to see Nicola and Ray, and John was just saying it's a pity Yakir wasn't in this photo as well. But I also acted quickly, and I saw a picture of Justin's picture he took yesterday is right there, so we can admire the beautiful 90-ish birthday photo. And then the second thing I want to bring your attention to is, of course, the funding for this work, but also the titles. So I think that maybe it's appropriate for the last talk of the conference to talk not about what has been done in the past, but looking forward to the future, what new discoveries lie ahead of us. As Daniele was saying, how dare you say beyond superoscillation, but I'm going to be so bold as to say maybe it's not the last word in physics and something new could come after it. So let me begin just by thanking all the people that I've worked with on these projects over the years. Many of them are here today, and you recognize many of their faces, so thank you all for the collaboration. It's been a lot of fun. I want to give a plug for our journal. This is the Chapman Journal Quantum Studies. I manage this journal together with a great team of editors, some of whom are here today. I just want to invite you to contribute to any papers relating to the foundational quantum mechanics or philosophical papers. These are all welcome and encouraged to help elevate the status of our journal, which I might add has grown tremendously over the past several years. And so I've been really proud with the work we've done with this journal. The second plug I want to give is for a book that I've written. So over the past 3 years, I've been working hard with my colleague Irfan Siddiqui at UC Berkeley to write a book about quantum measurement. So the title is Quantum Measurement Theory and Practice. And this book is done. So I just got page proofs back from Cambridge the past week. And so we're eagerly filling in the page proofs. So I'm optimistic, but not promising that by the end of the year we'll have this book published. And I'm really excited about it because I think it fills a really big gap in the literature that people simply don't know about. It doesn't matter how many papers you publish, people don't read your papers, they don't learn. And so my hope is that even though you don't read my papers, maybe you'll read my book and then learn something. And so just to kind of provoke things, so here's a picture of Irfan and I hanging out. We're celebrating in Laguna Beach after we finish writing this book together. What's the book about? So here is the subject flow of the book. You'll see it's divided into fundamental concepts, advanced topics, and then application and implementation. And if you look at some of the subheadings, you'll see things that we've been talking about at this conference. Most of the things are in the fundamental principles category, things like wave function collapse, generalized measurements, and then weak values, weak measurements. That's all in the fundamentals. But then the things that Howard loves to work on, and he's been a pioneer of the past years, are also there. Things like continuous quantum measurements, diffusive quantum trajectories, quantum jumps, Lindbladian equations, all that's there. And I think what's really, for me, motivating about this book is that we start with experiments. We start with phenomena in the laboratory, and only then do we begin to formulate theories and mathematical formalism to be able to explain the phenomena. And my co-author Irfan is an expert in superconducting quantum circuits, and so he really adds that experimental balance. I think it makes for a very fulfilling and motivating book. And then finally, we talk a lot about supporting technologies, things like how do you build a quantum amplifier? What's the best quantum amplifier you can build? Not only theoretically, but then how do you do it in practice? What's the circuit you would write down to build such an amplifier? How is it done? So that's all there. And so if you're intrigued by this, I encourage you to keep your eye out for it, and hopefully it'll be published.
Quick question.
Yes, Paul.
For those who can't wait, any chance of getting a PDF of your proofs? We promise not to sell it.
All right, Paul, on the black market, come talk to me afterwards. And then but also I think we begin and also end with things that can be read by everyone, not just advanced students of physics, but any person interested in the history of this field. What are the important philosophical issues that arise are all there for the taking. And just to kind of help grab you, if you're not yet grabbed, I've listed a series of questions on the left-hand side as a kind of quiz for you to look at and ask yourself, can you answer all of those questions? Because I'll wager 99% of physicists cannot answer all of them, and that probably some of the few people in the world that can answer all of them are sitting in this room today. So I just want to kind of put those things that if you read my book, you'll be able to answer all of those questions with experimentally backed up formalism. Okay, so let me go on now. Happy birthday, Yakir. This is for your birthday. And I just want to talk about, we've been talking about giving presents. So over the years, I've been privileged to write a number of articles with you here. This is something I never dreamed about doing. So here's our first one. We wrote this in, what year was that? 2015, about Heisenberg scaling and weak measurements. We wrote this paper together in 2016 about weak values being quantum. You maybe remember these papers, Yakir. This paper about diffraction-based interaction-free measurements, we wrote this in what year? 2019 together. This paper about superoscillations in several variables with other people in this room, we wrote in 2022. And then finally, the last, fifth paper, also in 2022 about superphenomena, not yet published, a preprint, 5 articles together. What an amazing privilege. All right, next one to talk about is what I don't want to talk about, which is a subject I've beaten to death over many years, which is weak measurements and weak values, with all of these keywords given here. But I do want to touch on it because I think it's an important part of our story together about what we've done and the impact it's made over the years. So if I look at that picture, that's not my picture. I stole that from a very peculiar article that was published on a couple of years ago in the archive. I must confess, I've never seen another article like this before. It's written by a Chinese group of people. I've never met any of them before. It's on the archive a couple of years ago, and I call it the famous bibliometric paper, because what does it do? It's a paper about a review and a bibliometric analysis of research on weak measurement research over the past decades. So what they do is they go through the literature and say, what's going on in this field? What's happening? What are the big developments? Who are the big players? And I think the motivation was to show China is also a big player in this game. Let's hear the kind of, because this is the last talk of the conference, for your amusement and entertainment, and also I think it's kind of fun to see, I'll give you a few snapshots of this paper. Most cited countries, most relevant affiliations, most relevant authors. So USA, we're number 1. China's number 2. Japan's number 3. France number 4. Most relevant affiliations, the University of Rochester, and then the Scientific Technological University of China, then Chapman University. Of course, what's happened since 2021 is that the first category and the second category have merged, making one big institution working on this field. And the most relevant authors, I'm embarrassed to say it's not Yakir Aronoff. Sorry about that, Yakir. It's me, followed by John, followed by Justin Dressel, and so on. Other funny things, author, local impact by total citation. I'm not exactly sure what local impact means. I'll let you read the paper. Again, I'm embarrassingly number 1, followed by John, followed by Justin, David Starling, Chinese author Bob Boyd. You see some of the names you recognize, Nicholas Bruner, Leo DiCarlo, and so on. And then again, the most active authors, again, embarrassingly me. And the conclusion, the United States is a major contributor to this research. The University of Rochester, this Chinese University and Chapman are considered excellent institutions. They're the most high citation authors. And their conclusion is Andrew N. Jordan is a prominent researcher in this field. My conclusion is I've written too many damn papers on this subject. Okay. But again, these are all gifts that Yakir has given us that we've been able to give back to him. All right, so what's the topic of my talk today? Getting to more substantial things. What I want to do is I want to... Yes?
I just to show the growth of the number of publications in that area.
Yeah, I have shown that in previous articles, but it's true that the number of citations to your original paper has gone up like crazy, and of course it started mainly with the experimental papers on the weak value amplification. That's when it really took off. All right, but I want to talk about not the old stuff, but the new stuff. And what I've put together here is a sort of potpourri of different topics, all related to superoscillations. And there's going to be something here for everybody. So if you're a pure mathematician, I'll give you something. If you're a theoretical physicist, I'll give you something. If you're an applied physicist, I'll give you something. If you're an experimentalist, I'll give you something too. The philosophers maybe are left out. I apologize to the philosophers. But all right. And so the topics I'll touch on is a super overview, and I've managed to cram every single topic to have the name super in front of it, which reminds me of a story that one physicist, I think it was my thesis advisor, once commented that the physicists have a very poor imagination when it comes to naming things, the most egregious example of which is the superconducting super collider. But I've managed to top that by putting super on every word on this slide. All right. So we're going to start just by reviewing what superoscillations are very quickly, because we already had a number of excellent talks about this in this conference. I'll talk about what supergrowth is. That's my own invention. Super approximation theory, an invention of mine with my PhD student Tathagat. Superquantum, this is this paper we wrote with Yakir, Daniele, and friends. And then something completely different that's not really related to superoscillations, but is sort of field adjacent, is what John talked about. I'm going to add some more details about the super radar he talked about the other day. So let's begin just with a quick review of superoscillations. What are they? Well, the basic idea is very simple. You take a Fourier series, like you learned about in college, and you bound the number, the frequencies. You take a minimum frequency, you take a maximum frequency, you put whatever coefficients you want, and we define that as a band-limited function. If you go to the frequency space, it has compact support in the frequency space. And the idea is, if I look at this function and I plot it as a function of x, there may be, if you're lucky, some regions of x where the function locally oscillates faster than the fastest Fourier component. And this phenomena is called superoscillations. And the example pioneered by Sir Michael Berry and Yakir and friends, including Sandhu, I don't know if Sandhu is here, has this very simple example that we've heard a couple of times about now. And the idea is that if I Taylor expand that, I have n as the highest Fourier number, but locally around the origin it goes like e to the I a n, where a is bigger than 1, so the wave number is larger than the highest Fourier coefficient. All right, good. So the way I think about it is I think about it a slightly different way. Yes, so here's a simple example. So this comes from Berry and Popescu's paper, and they plot this function, and they show that around the origin you've got these wiggles that are faster than the fastest Fourier number. But there's a big trade-off, because this is on a log scale, so these are very, very tiny oscillations on the scale of the function. So they're exponentially suppressed, and so this gives a challenge if you want to use these for anything practical. So let's talk about that now. Now, Andrew Briggs mentioned the other day he was really excited about what about using this for lithography or for super resolution, things like that. You're not the first person to think about this, but it's a great idea, and so people have been working on this. Can you take mileage out of this phenomena and put it to use? And the most, I think, simplest way of doing that is with optics. So the idea is you have an object intensity, you have a point spread function, and that creates an image on some optical system. And the idea is that if I use light of a certain wavelength, say I use red light, 660 nanometers, I cannot resolve objects that are smaller than that wavelength because of the Rayleigh diffraction limit. But, however, if I were able to create a superoscillation using only lights of frequencies red and longer wavelengths, I could create a local wiggle that had the frequency of 440, a blue light, and be able to then resolve things if I did clever processing. So that's the basic idea. And so this is important practically for building more powerful microscopes given the optical constraints. And so what you do is essentially you sacrifice intensity for improved spatial resolution because you want to get this fine detail of your image. Now, people have done this. There have already been experiments that exploit this effect. These are already 2018 experiments. I mentioned two references here, one in Optica, one in applied optics. And what they do is they create a certain kind of optical mode called Laguerre-Gauss beams, and they use higher order modes of these Laguerre-Gauss beams, and they plot them here as a profile view, and you see that this is the highest harmonic or the shortest wavelength of the light that's being used. Nevertheless, the profile has these higher frequency oscillations that they then use and exploit to be able to get finer resolution. So this is actually using some biological microtubule as the object and showing that one can indeed obtain finer resolution using the superoscillations than you could without. Now this is really intriguing, but there are many challenges with this approach. So one of the challenges is, we talked about earlier, that these are exponentially small oscillations. If you go away from this, you get these huge side lobes that pop up. So they have to go to extraordinary lengths to get rid of the side lobes so you can focus on these little tiny oscillations, and that's a problem. And so that maybe practically limits this effect. Nevertheless, it allows sub-wavelength resolution in incoherent optical imaging. So let's talk a little bit now about my idea. So I was sitting at the conference that Daniele and friends organized maybe 4 years ago, and I was listening to these papers, and I had my own idea, and I was puzzled because these experimentalists were trying to get rid of these huge side lobes, but that's where all the light is. And the question is there really none of the resolution in those side lobes? And I asked if that's really true. So do we have to sacrifice signal to noise to get enhanced resolution? And so I came home and I thought about that, and there was a proceedings article from this conference, so I wrote this paper titled Super Resolution Using Supergrowth and Intensity Contrast Imaging. And the task I had was very simple. I just wanted to distinguish 2 point sources of light, not with superoscillations, but this effect I call supergrowth. Now, what is the supergrowth? The idea is it's possible to use another feature that's also been undiscovered, but there all along in these superoscillatory functions, which is if I can define a local rate of oscillation to be k of x, I could also think about a local growth rate. What's the intensity growth or decay of the function defined by kappa of x? So I can write any function in this way using these k and kappa functions. So I can define them then as the real and imaginary parts of the logarithmic derivative of this function f. X. Yeah, so this is a dummy variable x prime, and I integrate it up to x. And so the idea is that how can I define superoscillations? Well, that's when the local wave number exceeds the band limit of the function. So I can define supergrowth as when this function kappa also exceeds the band limit of the function. And why would I think that? Well, I had another idea. So if I just take that function Yakir thought of many years ago, and I plot the logarithmic derivatives, and I draw the band limits on this diagram, so what I see is that the local wave number, that's the superoscillation, that indeed exceeds 1 in normalized units here at the origin. It goes up to 6 for this choice of parameters. But then it goes outside the superoscillatory region here. On the other hand, if I plot the kappa parameter, you see that kappa, it's the blue curve, it also exceeds this line as well, but at a different location. It's not at the origin, it's at some slightly different place, and it goes up to a factor of 3 here. So the idea then is that we define the superoscillation region when the local wave number exceeds the band limit, and the supergrowth region is when the local growth or decay rate exceeds the band limit as well. Now, why did I think this could be useful? Because I remembered in the back of my mind there is a really nice optical technique called evanescent wave microscopy. And the idea in this technique is that if you get really close to a sample and you go into an evanescent wave region where there's forbidden propagation, you get exponential decay of the electric field into the sample. And because the rate of decay is faster than the wavelength, that gives you enhanced resolution of the spatial features of the object you want to detect. So the idea, the promise of this new idea I had was that you can do the same thing, you can do the same kind of near field scanning optical microscopy stuff, but now in the far field, no longer in the near field. So that was the key idea. So you can go through the math and you show that you can look at the maximum value of k, and it goes like 2a over 2, and so the logarithmic intensity goes like 2 kappa. So what we find using this classical example that Sandu Popescu wrote about, together with friends, you can get the same resolution for large A, but here's the important point. You get much more intensity because you're at a point on the intensity curve that's much higher than the superoscillatory region. So this promises you the same kind of resolution, but because you have better signal to noise, you can overcome many of the obstacles that were encountered before. So I'm going to take the opportunity to announce some new results. So I want to give you some hot off the press stuff here. So we had just published a month ago, or put on the archive, a paper with Tathagat, Abhishek, and these are my students, together with Nikolai Mivakis, about using this method not to just distinguish 2 point sources, but to actually do sub-wavelength object imaging. And so this is the article we posted on the archive. Here's the archive number if you want to read more about it. And it shows a way of being able to reconstruct images that are outside of the band limit of your function. So that's result number 1, announcing the results as a theoretical paper. But I'm also pleased to announce experimental results as well. I hope Andrew will be sufficiently excited by this. So this is a paper not even yet on the archive. I hope it'll be probably by next week, but I talked to my co-authors and they said they'd be honored for me to present it at this conference. So the title of the article is Experimental Realization of Supergrowing Fields. And again, this is with Nick and his group and together with Tathagat. And what do we do in this paper? Well, we have an experimental apparatus. So Nick is at the University of Rochester, where I was previously. And the basic idea is that we use some source that has a band limit, and we're able to create fields in the far field that have supergrowing intensity. So this is, again, far field optics here, what we're doing. That's the schematic. Here is the actual device. The secret sauce here is we have lenses and laser. The secret sauce is the spatial light modulator, where we can essentially use holograms to be able to encode phase structures on the spatial light modulator that can create whatever optical field we want within some limits. That's then taken through lenses, a pinhole, and then imaged onto a detection plane. So here's a pinhole plane and a detection plane. And that's basically the apparatus that's being used in the experiments. Now, here's what we're able to accomplish. We're able to accomplish, this is the data. So this is, what I'm doing is here, I'm plotting theory and experiment, plotting the profile of the intensity. We're using intensity measurements versus the optical axis of the image plane. And what we see is that we're plotting here, what am I plotting? I'm plotting, first of all, I'm plotting the intensity as the black dots. I'm plotting the growth rate, kappa, and then the dashed lines are the band limits, the maximum value of the bands that we've imposed upon the experiment. And the upper row is with supergrowth features that we've engineered into the profile, and the lower panels are without the supergrowth, showing that we have control over this feature. On the left is the theory, and on the right is the experiment. And you see we have very good ability to control this feature and also very good ability to predict it. We have good agreement between these two different theoretical and experimental approaches. And gamma here, this gamma parameter is simply the ratio of the supergrowth rate as a function of position divided by twice the band limit. So if it goes above 1, that means we're in a supergrowth region. Okay? So in the experiment, the maximum value, I think I showed before, they were able to get superoscillations of maybe 3 or 4 above. Here we're able to get about 18, a factor of 18 above the band limit in this experiment. So the main conclusion you should take away from this plot is that it demonstrates our ability to generate and control supergrowth in an optical experiment.
What are the A and the B, Andrew?
Yes, so A and B, This indicates, this is actually this indicates the intensity. That's the optical intensity. Blue, that's the kappa sub I, that's the supergrowth rate. And what we're showing here is that basically we're looking at the same kind of plots, but then normalizing it in terms of this gamma parameter. So we're dividing essentially by this this band limit to show how much further we can exceed the band limit on these on this other graph. So B gives a little bit easier way of visualizing the data.
So A and B convey the same information.
Yeah. Okay, good. Now you might say, how on earth, Andrew, are you able to get this kind of control to be able to bring out these functions? I'll just mention, here's another set of data where we can control also not only the height of the supergrowth region, but also the width. So that's also, when it comes to doing super resolution, you want not only high values, but also large width to be able to have a large region of be able to do this. And it just basically shows that we have control over that as well. So this is the full two-dimensional scan, this is experiment, this is theory, and this is the actual profile of the optical beam on the left-hand side. And on the right-hand side, we're plotting our kappa parameter. So whenever the white region is simply when this gamma parameter exceeds 1. So you see that we have good regions of control, and if I take a slice through that two-dimensional plane, we generate these plots over here. Okay. So we can control not only the height, but the width. And then you might say, how can you program this spatial light modulator to give you what you want? How do you have this control? And this is going to take me to the next topic of my potpourri of topics that I think you here will find interesting, which is superapproximation theory. And the thing I was frustrated about when I first learned about, and we come back to that in a moment. So again, we have a paper on this. This is just last month, or 2 months ago, together with the Thoggett. The title is Beyond Superoscillation, General Theory of Approximation with Band-Limited Functions. The idea here is that I was frustrated when I first learned about superoscillations, because people could give me specific examples. Here's a function that superoscillates. Here's another one. Here's another one. Maybe 10 of these examples. But I said, isn't there some kind of general rule, or how do you generate these in a more general way? And it turns out people had thought about that in the literature. In particular, Achim Kempf and his collaborators have done this quite a lot. But we found another really nice way of doing it. And here is our solution. So the problem is that existing examples are ad hoc, small in number, and uncontrolled. Our solution to the problem is to create a new theory of approximation using the band-limited functions. And we use this theory to be able to control those properties I was showing you in the previous slides. So what's the basic idea? We restrict our space and consider only band-limited functions between two frequencies, so omega 1 to omega 2. Then we want to pick a function not in that space and approximate it as best as we possibly can, but in a finite interval of the real space. So schematically as listed here, we have some space of functions that are band-limited. We take a function outside this space. For example, if this has a band limit of a frequency of 1, but I want to oscillate to do something like cosine of 10t. This is not in that space, but my job is to approximate it the best I can in some finite interval. So the black region here is I want to approximate it, and outside that region, I don't care. It can do whatever it wants. So that's the task we put in front of us. And in the interest of time, and also not boring you with the details, I'm not going to go through all the mathematics, but I just want to sketch the features of the solution. What we do is we essentially start with mapping this frequency interval of interest to an interval -1 to 1. And then the key idea here is not to use an oscillatory approach, but to span this space using orthogonal polynomials. So by using this polynomial, it goes into a kind of dual description of the space. And so we can write any function in the space as some linear superposition of orthogonal polynomials on that interval. And if we happen to choose the Legendre polynomials, then it turns out that only the first two coefficients of that expansion are sufficient to completely specify the degree of superoscillation or supergrowth at the origin of the real space. That's a real benefit of choosing this particular set of orthogonal polynomials. And then what happens is if we convert from the Fourier space to the real space, the Legendre polynomials Fourier transform into spherical Bessel functions. So those are the Bessel functions you often find in solutions to spherically symmetric problems. And then once we do that, we have, again, that expansion in the real space. What we do is we define an L2 norm error between the target function and this expansion in terms of spherical Bessels in a finite interval. We extremize that error to try to minimize it, and then we find a matrix equation to invert to be able to choose for us the desired coefficients we want in order to get the function we want in that space. There's some details. It becomes ill-conditioned if you have a large number of terms, but the main finding of this program is that we find excellent agreement between the target function and the band-limited approximation, but at the cost of exponentially large disagreement outside the interval. So just to drive home this point, I'm going to give you some simple examples here. So what I've done here is on the top plot, I've only used band-limited functions that have a maximum frequency of 1. I'm trying to mimic cosine 10t, e to the 10t, and even go crazy, a step function. How can I do that? If I execute the program I just described to you, this is the approximation using only band-limited functions. We have excellent agreement here, excellent agreement here, pretty good agreement even for the step function. That's not even a differentiable function. Now, what's the lower panel all about? Well, that's what happens outside -1 to 1. If you think about other values of the parameter, it goes crazy. And if you look at the scale here, this is 10 to the 9, 10 to the 11, 10 to the 12. So it goes nuts outside of that region. But nevertheless, we can get exquisitely good agreement within the region we want. So I was really happy with this theory because that gives us a very general way that goes beyond the concept of superoscillation to really do any kind of thing we want in this band-limited approximation.
Sorry, Andrew, I just missed what is the actual band-limited numbers?
1. In this example, it's the frequency of 1 is the band limit. Anything between -1 to 1. So the highest frequency would oscillate on the scale of 10 times that plot.
Andrew, I have a question. The very right column, top panel and bottom panel, you showed on the top panel to 0.5, but it is flat on the bottom panel up to say 5 or 10. So how much is the difference at that point? Above 0.5 to say 5?
Here to here, you mean?
No.
Here to here?
Yeah.
The answer is 10 to the 12th. That's how big it is.
No, the question is not that. See, you show the horizontal line on the top panel till frequency 0.5. The x-axis?
This is not a frequency, this is a position.
Position.
Yeah, or
But
time.
On the bottom one, it goes flat to 5, for example.
Yeah, so
From 0 to
I'm
5.
plotting it on a larger range down below.
Yeah.
Here it's -1/2 to half, here it's -20 to 20.
Yeah, so if you will go on the top panel beyond 0.5,
Yeah.
how much will be the difference?
I didn't show that, but it starts to explode pretty quickly. Pretty quickly, yeah. Yeah, another quick question.
So when you try to approximate a step function using a Fourier series, you get this Gibbs ringing, Gibbs phenomenon kind of thing, right? And you see similar ringing here. How do the two compare?
Yeah, it's a good question. There's this classic Gibbs phenomenon in Fourier series. This is the same kind of thing. We haven't looked into it in detail, but it's a good question. Yeah. Yeah. Good. All right. So that's super approximation theory, and we use that to be able to get the exquisite results here with the experiment. But now I want to. How am I doing on time? I think I'm doing pretty good. I want to go now to talk about superquantum, and this is the work that I did and worked out with Daniele and Yakir and friends, Fabrizio, a long list of friends. So here's the list of friends here, together with Nick. And the idea I had was that we have this notion of superoscillation, but it seems to be a very general idea. Can I generalize the idea of superoscillation to anything in quantum mechanics? So now we're back to quantum physics. So before it was just wave physics, now back to quantum physics. So what's the idea here? The idea is, let me motivate that. Let's go back to our wave function now. It's a band-limited series of plane waves. And I remember I defined the local wave number as this thing, the logarithmic derivative of the function, imaginary part. And if, for example, if I have only one Fourier coefficient, then this thing will return the wave number. And remember the definition, this function exhibits superoscillations if k of x exceeds x exceeds k max. That's the definition of superoscillation for me. So how can I generalize this notion? So remember, this right now this is only a property of some function. Doesn't have anything to do with physical anything physical immediately. But the thing I want to point out is it's closely to the momentum operator. So if I rewrite that logarithmic derivative as the real part of this weak value, It's exactly the same thing. Now let me break that down for you a moment. I take the ket that is a bounded series of eigenvectors of momentum. I take the operator P, so this is like my pre-selection, this is my operator, and then I post-select on a position X, just formally, not physically, but just mathematically. I divide by the inner product of psi with X, I take a real part, lo and behold, it's exactly the same thing as this K of X up to a factor of H bar. Once you see that idea, then it becomes very easy to generalize. Superoscillation is just the real part of the weak value of the momentum. Supergrowth is just the imaginary part of the weak value of the momentum. Very simple. Once you see that, then it's trivial to generalize it to any operator you want. Now take some operator O, your favorite operator in quantum mechanics. I take its eigenspectrum. I define a ket that takes only eigenkets of this operator, but bounded between some minimum eigenvalue, some maximum eigenvalue. That's my pre-selection. My operator is the O, and then I post-select on position. Boom. I define this as exactly the analogous thing to superoscillation for any operator O, and I say that the operator exhibits super phenomena if the local value of the operator either exceeds the maximum eigenvalue or goes below the minimum eigenvalue. And you see it's very clear if you understand weak values why this is interesting, why this happens. And so we've worked out a number of examples of this that are really interesting, but in the interest of time, I'm not going to give them here. But if you're really keen, I can show you some really cool examples of this phenomenon. In the spirit of the beautiful mathematical talks from Irene and Fabrizio and Daniele, they were very keen on trying to generate a superoscillation everywhere in space by taking some kind of formal mathematical limit. For them, that's really the beauty, that's really what's exciting about the superoscillations. So to please my mathematical friends, I found an example, a physical example, where I can generate a formal series of physical potentials where the energy of the particle is bounded below a particular value for every single value of the sequence, but in the limit that I take that sequence to infinity, I generate a particle with infinite energy, even though every member of the sequence is bounded. Sounds like a magic trick. So if you want to hear more about it, I'll tell you later, but that's a little teaser for later if you're interested. All right, so the last topic I want to talk about is the super radar stuff. So again, this is distinct from superoscillation, so you don't get confused. This is not superoscillation, but it has certain adjacent properties. So here's the paper John talked about the other day. This was only published a couple weeks ago, 2nd of August. The title is Super Interferometric Range Resolution, Physical Review Letters, editor's suggestion, and featured in physics. There's a beautiful focus story in physics called Radar Resolution Gets a Boost, written by Catherine Wright, who is the deputy editor of the Physics magazine. If you don't do anything else related to my talk, read any of my papers, I don't care, but read this little article in physics. It's beautifully done. Anyone can understand it, and it gets the science right, importantly. All right, so what's this all about? The other thing I want to point out is this is kind of funny, just as a sociological thing. Look over here at this weird little rainbow. You probably never even look at it in your life because it's never relevant for you. This is something called the altimetric score. This tells you how popular your article is with the press, with newspapers, with blogs, with tweeters. I don't do Facebook, I don't Twitter, but I know that these things exist. I guess it's called X now. But if you look at this number, it's 145. And you say, what the heck does 145 mean? Well, I looked up my altimetric score for my Nature article. It was on the cover of Nature. That had an altimetric score of, let me see if I can find it here, 113. That was published in 2014. This paper was published 2 weeks ago. It has an altimetric score of 145, which means it's in the top 98% of all articles covered in terms of its popularity and interest in the press. Or, yeah, top 2%, exactly. 98th percentile. Thank you, Ephraim. So why are people excited about this, and what the heck is this guy doing with his little bicycle wheel over here? First of all, let me just acknowledge my collaborators. This is with John, but also with Akim Kempf, who is in Canada at the Perimeter Institute, and his student Barbara Soda. And how did this all come about? Well, Daniele maybe remembers we were sitting in Cetraro having lunch on the seaside cafe restaurant, enjoying ourselves after I had presented my supergrowth work. And Akim comes up to me and he says, Andrew, have you ever thought about doing this for landmines? I said, what the hell are you talking about, Akim? What are you talking about? He says, well, I had this kind of crazy idea with superoscillations that there's this problem that John talked about before, that if I take radio waves and I put them into the ground, if they're really long wavelengths, they go really deep into the ground before they reflect. But if they're really small wavelengths, they bounce right back. They only go about this far in, and then they bounce back. And that's a problem because you need short waves to get good resolution on things like landmines under the ground. So this is a really big problem. And so I thought I could use superoscillations to solve it. And my idea was, I have a band limit where I have really long wavelengths as the upper edge of my band, but I generate a superoscillation out here, and I could use this to do the resolution, but it still comes back out of the ground. Everything is solved, no problem. The difficulty is this amplitude of this is so small, the superoscillation, it essentially, any kind of absorption immediately kills it. So essentially the idea is dead in the water. He thought maybe because you have more intensity in your supergrowth, that would work. And so I said, that's great, that's brilliant. Daniele, we're going to solve the world's problems with our formalism, and off we went. So we started working on it together. I brought John Howell in because I said we should do some experiments too, and then the rest is history. But the thing I wanted to, excuse me, I wanted to just think. Of course, not only for this, but the Institute and their entire gathering. So thank you, Deb. Okay, so why is this important? Why do people care about this? If we can solve this problem, we can change the world. Landmine detection, archaeology, treasure hunting. We identify drones versus birds. We can take X-rays with radio frequency waves. How amazing that would be. Military, sorry, I had to redact that. This is being recorded. But the list here is long. We can do ultra long wavelengths. We can map the ocean floor with kilometer long waves. Ultra short, Yakir pointed this out in the car the other day. You can map the core of a nucleus using electron waves, sonar, it goes on and on and on. If we can crack this problem, it changes the world. So the outstanding problem is how do we get high spatial resolution with long wavelengths? The only problem is they all said it was impossible. And it was a lot of fun digging through the later literature with John, trying to look how many times this stupid equation appeared over and over again, and then seeing it in these various books. Waves theory indicates the best vertical resolution is 1/4 the dominant wavelength. With any vertical distance, any reflections will interfere in a constructive manner and result in a single observed reflection, on and on and on. So how to get around this? And indeed, I started telling people about it. And the solution, of course, is extremely simple interference. But I started to, as I told people about it, I got different reactions from different people. So I told my friend Joe Eberly, I said, Joe, I was there in Rochester not too long ago. He's a very famous quantum optics guy. I said, Joe, I found a new way of doing radar with John. The idea is that traditionally you have two objects, and how do I distinguish the distance between them? Well, I send a radar pulse, and I hear ping, ping when it comes back to me, and not just ping. And this is what they call how to do temporal resolution of two objects. We found a way of beating this resolution limit that I showed before, that the pulse has to be smaller than the distance between the objects. And he says to me, Andrew, what else could you possibly do? That was one reaction. I told this to Justin, and Justin said, I said, the solution is interference. And he said, interference? You mean to tell me that we've had 100 years of research of the military-industrial complex and the best scientists in the world, and they didn't see this? And it's not quite that simple. There's more than that. We have to think away from thinking about a time-resolved picture to an amplitude-resolved picture. Now, why is that important? And the problem is another story I had when I told Andrew Briggs' colleague, I was chatting with Natalia Aries, and we were sitting in a restaurant in Vienna a month or two ago. And I said, Natalia, I have this great invention, a super radar I want to tell you about. And I say, well, the idea, and I said the same thing to Joe, and I said, well, the thing is you don't do temporal resolution, you do amplitude resolution. She said, well, Andrew, aren't you worried? Because this is radar, this is not an interferometer. You only get back a tiny amount of light. And this is exactly the point where I think everyone got stuck. Because indeed, if you say, how can I measure amplitude changes? I'm sending out some huge pulse of energy. It goes kilometers away, it comes kilometers back. There's some small scattering cross-section. I'm down 100 dB from the power I sent out. How can I distinguish between 101 dB and a 99 dB? It doesn't make any sense. You can't do that. You can do that in an interferometer, but not in a radar thing. And so the key idea number one is to disregard the overall size of the return signal and just use self-referencing features of the pulse. And key idea number two is to not approach it from a temporal resolution, but from a metrology perspective. You think about it as trying to do parameter estimation. That's the second key idea. Okay, so here's the paper. I'm not going to repeat John's talk. I'll just flash the high points. What I want to stress about John's talk that was so delightful to me is that he did this experiment in his office. He had a function generator, he had some BNC cables, he had an oscilloscope, and he published this paper. Amazing. Here's the idea. He created some pulse, band-limited pulse that looks something like this orange curve. We also played with these triangles. Forget the triangles for now. You look at the Fourier amplitude, there's a band limit. After you reflect it off of two objects, say object 1, object 2, there's this area gets reduced. This area is not reduced, so you can use that feature to then create an estimator to be able to figure out how much distance there is between the two objects. Here's the data. This is the signal he defines versus this is all in the sub-wavelength resolved point. Initially, there's some kind of quadratic behavior. Then it becomes linear. So this is nice. It's a linear estimator once you're away from 0. And then you get these very fine resolution onto how apart these two scatterers are. And I'm not going to give you the quote from our paper. I'll let Robert Garisto, Lev Weidman's favorite editor, take the credit. He tweeted this. He's the editor-in-chief of PRL. He tweeted this out. We experimentally demonstrate our system can resolve two depths greater than 100 times the Edinburgh bandwidth and measure the distance to approximately 20 microns, 35,000 times smaller than the Rayleigh resolve limit. That's the main point.
How does the 100 translate to
So there are two questions. One is, can I resolve it, period? How far apart do I have to move it to resolve it? That's the resolvability question. And then once it's resolved, the second number is you're still sub-wavelength, but then how finely can you measure the distance between them? So there are two questions. So now my friend John, he's a man of action. Once he sees something, he just latches onto it like a lion and goes forward and does it. And I said, John, I think we can do better. We have some other ideas. He's like, no. We just got to do it and publish it, and then we'll break the limit, and then we'll do more, which, of course, was the right thing to do. But then, of course, people have follow-up questions. Everyone is like, well, how does this work? And I'm going to try to answer the follow-up questions because I worked really hard and posted this paper on the archive. This is just with John and me. I posted this on the archive Friday. It appeared this Monday, so I could present it at this conference. So I'm going to announce new results. What's the point of this paper? Well, the title is Fundamental Limits on Sub-Wavelength Range Resolution, because the question is, how low can you go? What's the best you can do given fixed metrological resources, given the type of problem you're trying to solve? So it was clear in our paper that we could do a lot better if we tried to optimize things. Different pulse shapes, different ways of data processing. And Ephraim Steinberg, brilliant man that he is, asked this question to John just the other day. It would be good to see, and I'm paraphrasing Ephraim, it would be good to see if you can specify where the advantages come from. Pulse shape or data processing or both. On point, excellent question. And indeed, in the last line of our paper, we say in the future work, we'll explore the fundamental limits of this technique, as well as apply this method to more realistic range tasks in the field. The paper, unfortunately, is very mathematical, so I'm only going to give you the basic ideas. The idea is we consider two different models. One is field detection, the kind of thing that John did. We have some kind of amplified output of an electromagnetic signal plus noise from the detector. This is applicable to radar physics. and also photon detection. So imagine you did time of arrival detection of photons, for example, LiDAR, or if you did like Yakira's idea with using electrons with their wave function, time of arrival, do photon detection. And for both of these things, we have a very basic task in the simplest possible case. Suppose you have two equal reflectors that are separated by some distance L, described by some function f. What's the best you can estimate this value of L between these two functions? That's the problem we tried to solve. So the idea is that, but there's a very important thing that I have to stress here. So just like Natalia Aries' comment, Andrew, you don't know how much light you're getting back. What was great about John's experiment is he had a reference. He had a reference that there was a part of the function that didn't change, and you could use that as a self-reference thing. What we can do here is we can do the same kind of thing. What we do is we simply normalize the function. We say we take whatever function you get some pulse back, and you just normalize it. You make it the area square integral area is 1. That's basically the measure says how much power do you get back in the pulse. And then you scale up everything. You also scale up your noise of your detector. And you say that's the signal. So the point is that this normalization also contains information about the parameter L, but we're not going to allow ourselves to use that. We say that's cheating. We assume it comes back from some distant thing. There's lots of loss in between. We don't know the absolute size of the function. We just want to look at self-referentialing the shape of the function. That's the only thing we're going to use. And so, for example, if you have John's function here, you have something like this that you send out. You get back a much smaller version of that, but then you have some noise from your detector that's on top of it of some amplitude, and you're trying to then figure out what L is for this function. So sigma then specifies the noise contribution, how big the noise is of this rescaled signal. And I'm just going to give you one formula, maybe the most important formula. We're going to throw away the radar textbook answer, and we're going to give you this formula instead. And you say, Andrew, that looks like some crazy formula. What the hell are you talking about? Let me unpack it for you. So the derivation uses, we look at various different approaches. Some Fisher information approach, some overlap of matrix of vector approach, and some quantum Fisher information approach. But here's the result. So in the deep subwave limit, the relative uncertainty of the L, how small I can figure out the uncertainty over L, is bounded by the ratio of two things. So the sigma is essentially the scaled RMS noise of the detector. In the denominator, there's the number of trials, number of repetitions of the measurement appears here with L. This is again the parameter squared L. And there's this funny delta thing with this funny symbol. What is this? It's something weird. It's the variance of the second derivative of the function in the original function f. It's something weird you don't usually see in metrology. So why does this appear? And I can give it sort of a very intuitive way to show kind of why it appears with a simple example. But anyway, before I go, I just want to, this is maybe the main, most important result of the paper. This is in the field detection case. For the photon detection case, you get something similar. There's a different prefactor, but the same kind of thing occurs. So then to answer Ephraim's question then, how do we get the most bang for our buck? We want to maximize the variance of the second derivative of the pulse shape to get the best resolution. And when this thing, so if you calculate this, it's typically, in the best cases, going to be comparable to the band limit squared. And so that implies that this combination L squared delta is less than 1. So if I look back here, if L squared delta is less than 1, I want to get this quantity to be as fine as possible. And so the way I can do that, though, is if I have good signal-to-noise ratio, if the number of repetitions divided by sigma is much bigger than 1, then I can still get very good relative error on the parameter. So another way of seeing that is if I plot this is actually the Fisher information calculation we derive. If I plot the Fisher information versus the scaled value of L in the subwavelength limit, the true value of the Fisher information starts at 0. So when the things are on top of each other, you don't get any information. It increases quadratically, and then the true value has a little curve downward like this, whereas the quadratic approximation continues to go up. All right, so the quadratic approximation, that's just the number I gave before. That's this thing. That's the prefactor of the quadratic approximation. Very good. So let me go on. So let me give you a very simple example to help you explain this. Oh, yes, Sandhu.
That is a lower bound. Can you come close?
Good question. I'm going to get to that. So there's the bound, and then there's how good you can do. Let me get to that in my next slide. Simple example. Take the very simplest band-limited function you can think of, sine kx. The band limit is k, right? So what do? We take sine kx, a plane wave, we bounce it off of our two reflectors, and I get this combination like this. I get x plus L over 2, x minus L over 2. I can use some simple trigonometry elementary school kids know, and I can write it as sine k0x times cosine k0L over 2. Now, if this were an interferometer, what does that mean? That means you take your waves and you decrease the amplitude a little bit. And if you had an interferometer, you could then fish out from that amplitude how big the parameter is. But if you say, no, I don't allow myself to use that because I'm in a remote sensing environment, I only get a little bit of light back, I'm going to disregard the overall amplitude. Once I renormalize that function, it becomes exactly the same as the original function, so I get absolutely no information about what's going on. And indeed, if I calculate the variance of the second derivative of the function using this guy, I get the answer 0. So that gives a little consistency check and just illustrates why this is a more subtle problem. So yeah, the point is it's useless in radar. Good. So further direction. So that's the main idea. We did a bunch of other stuff in the paper. I don't want to take your time to go into it. So coming to Sandhu's point, what you can do is you can explore various different estimation strategies. So the one we looked the most at is maximum likelihood estimation. So we have a model for the signal plus noise detection, and what we do is we maximize the likelihood given the data given observed data for a given value of L, and by maximizing the likelihood, that gives you a way of approaching asymptotically this Fisher information bound. Now, what's interesting about that is when you actually work out the maximum likelihood expression, something that I didn't expect but is very nice is that what comes into it is you basically comparing a vector of an estimated L together with a true L as like an inner product. And what you see is that when the estimated L reaches the true L, that maximizes the inner product, and anything else, because they're normalized vectors, decays away. And so what we show is that this gives you a way of optimizing the information about the parameter given a certain waveform. The other thing I want to say about that is we also looked at other estimation strategies. We looked at Bayesian estimation, and you might also think about using either a uniform prior or Jeffreys prior to be able to do other kind of estimation strategies. But because we have the luxury of large amounts of data, like if you're doing ground penetrating radar, you just keep measuring. The bones underneath the ground aren't going anywhere. You just keep getting data. So we consider other metrics. So an overlap metric of distinguishability, which also turns up again in the maximum likelihood. And we also thought about measuring in different bases. What if you didn't do position measurement, but you did momentum measurement? This means you would maximize the quantum Fisher information. This is like a little bit like what Men-K Sang did in his work on incoherent optical imaging. And then what you see, it's natural if you can write everything in the quantum mechanical formalism. And what you find there is you actually have to maximize the variance of the momentum squared in the function f, which is basically the same thing as the second derivative. And so again, in some sense, the momentum basis is a more natural basis. And we also worked out some multi-parameter estimation because that's really important for our next steps. So I think I want to end here. So happy birthday, Yakir. I hope I gave a super talk. I introduced a number of topics that touch on superoscillations, but lifting off from the ground, move away from them as well. And we're just started. This paper on super radar is not the end. This is the beginning. We have much more work to do, and I'm looking forward to seeing where it takes us. So thank you so much for your attention. Jeff, you can handle my call on people?
Oh, sure. Justin?
So Andrew, I can't help but notice, I don't know if you noticed this, but your second derivative variance term that you're having to maximize in this happens to be exactly the quantum potential of the signal f integrated over the pulse.
Well, there you go. A missing connection. It was there all the time. You have to give me a reference on this, Justin. Thank you.
Yeah, it's something I was just discussing with Deidre, so I'm amused that it's right there and the central feature.
That's the main result, yeah.
work. It's really exciting, and I look forward to learning more about it. Side comment to you, I just got an email this morning from my student Noah pointing out that he discovered a relation between that so-called weak variance and metrological sensitivity. So I think we're all noticing the same thing here. I did have one suggestion, comment, question for you guys. Since your bound comes from this Fisher information approach, it reminds me of something that we ran into with Bankay's original super resolution business, where he showed that the information vanishes as L goes to 0. You had a formula where things are diverging as 1 over L squared. And the interesting thing is, if you did classical imaging where that Fisher information went to 0 as L went to 0, the best estimator you could come up with didn't have a divergent uncertainty, because the assumption for that bound is that you're using an unbiased estimator. And it turns out for these things that are positive definite, like a separation, eventually it becomes wise to use a biased estimator. So you can't make the uncertainty of an unbiased estimator vanish, but for the biased estimator, you can actually make the root mean square error get quite small. You still do better with the quantum approaches, but it just makes me think there might even be steps beyond your bound in some cases.
All right, Ephraim, this is why we invite brilliant people to conferences like this, so you can teach me something. So let's work more on this, and I need to learn more about bias estimators. Usually I try to avoid bias, but here, maybe there's a good advantage.
In today's climate, maybe
Fair and neutral, yeah.
Thank you. First, I want to comment to Justin, just to know that quantum potential takes similar form as Fisher information, expectation of Fisher information. So because of that, we have these relations. So it does not depend on quantum mechanics. Yeah, sure. I just want to say that, the super oscillations, you can see them, of course, with classical waves. But my question is that we know that super oscillations need to be, they are sensitive because we need suitable amplitudes, right, in general. So in practice, really commercial tools, how can you do that? Because of their sensitivity.
Right. So coming back, for example, to our experimental results with the super growth, for example, the reason we can do that is because we have very good control of the spatial light modulator. So what the spatial light modulator do is you encode a phase pattern on this modulator, and different versions of it either use sound or light to control the light fields that are coming out of the spatial light modulator. And so what we can do is we say there's a kind of reverse engineering. We say here's the profile we want. What is the kind of phase pattern we need to encode upon the spatial light modulator to get the features in the far field that we were really looking for? And so that is the thing that we have to encode, and the experimentalists encode into their apparatus. And the reason we can do that so well is because we now have this better way of handling different kinds of supergrowing, superoscillating functions using our band-limited function theory. So that gives us a very nice quantitative handle to produce whatever we want, to make the width of the supergrowth larger, higher, whatever you want. We can do that.
Yeah, and you really need super oscillations or super growth for this. Like if you have a additional modes that are behind it. If you have a convex sum of Gaussians, I don't know. Like you really can prove that you need super oscillations for getting the desired result.
Well, for getting this super resolution, you need features that are sub-wavelength. Yeah. That's the point. Mm-hmm. To get super resolution, you need sub-wavelength features. And so typically with Gaussians, if you add a bunch of Gaussians together, typically the width of the Gaussian can't be smaller than the wavelength. And so I don't think there's any, maybe I'll eat my words, but I don't see any way of adding Gaussians together to get that.
Mm-hmm. Okay, thanks.
Just kind of something sort of historic. I remember hearing long ago from a person named Aaron Lewis. He was at Cornell and eventually went to Jerusalem. How to try and use pipettes, which are ever narrowing, to send laser beams to look even at molecular structure. But the trouble in his approach was there was an exponential suppression because most of the weight gets reflected. So you are beating these things somehow in your approach? Was it a near field, you say? Now you're doing far.
Yeah, that's right. So the idea is that in the near field, if the wave is propagating like this, it tends to then decay exponentially with the evanescent wave, and that's your pipette effect. You get smaller and smaller light. But the nice thing is that if you don't go all the way down, if you put an object here, you can see things with in this direction that are finer than the wavelength. So that's the basis of this tunneling wave microscopy. In my situation, what I do is I don't go in the near field. I'm in the far field, but I use lenses and things like that. So the structure is like this. It's not in the longitudinal plane, it's in the transverse plane. So if I think about scanning across, there are regions of this field that go up exponentially faster than the wavelength. And that's the feature I'm using for super resolution.
Yeah, thank you so much. That's it. I have two questions. The one thing in that the basics on thing on the super resolution, and that how much robust to that such kind of waveform. In that the same slightly change on the paradigmatic thing on the waveform. In that how much affect to that in that super resolution. In the second question is,
Let me answer the first question, otherwise I'll forget it before I get to the second one. Well, the fact that we have good agreement between the theory and the experiment shows that there's a relative tolerance to imperfections. Right. You saw the agreement wasn't perfect, but it was pretty darn good. So that shows there's some, at least within experimental control, there's some robustness. Now these things are very delicate to create, and so if you screw it up, it's easy to screw it up. But at least within experimental control, it seems to be okay.
Okay, right. In the second question, now in the case, you consider on the spatial resolution only. In the time, but you talking about the relationships, the weak measurement, the weak value. In such kind of case, in that we replace to the space and the momentum relationship to the time frequency domain. In such kind of case, in that it seems to be pulse shape on that the pulse limited bandwidth that can be limited by somehow. In that case.
Yeah, that's a very good question. Maybe I glossed over this point, and I apologize because when I went to my theory, of course, what happens in reality is you get a waveform that comes in time, and you record the features as it comes in, and you get some kind of pulse in time that looks like this. Yeah. Now, what I was doing in my analysis is I set the speed of light equal to 1 and converted time to space, and that way frequency becomes momentum, because it's easier for me to work with position and momentum, but it's exactly the time and frequency space. So basically, I use the fact that this is a speed of light wave at c equal 1 to convert back and forth. So that I should have mentioned that, but I forgot to say.
Yeah. If that's the case, on the for example, frequency cone, such kind of another application. What kind of relationship do you do?
That's a great question. I thank you for asking that, Yutaka, because in our long theory paper I just posted, we have a section on frequency combs, and you can get really good resolution on frequency combs. Let me say just a word or two about that. Right. Suppose you have band limits here and here. What's the easiest frequency comb? It's just this. I get a e to the I omega t here, e to the minus I omega t here. Unfortunately, if I just have this, that goes back to my sine omega t example, which has 0 resolution. It's completely worthless. Right. But if I put a bunch of other combs like this, then it works really well because that's the variance of that second derivative. It works. And so, not to let the cat out of the bag, but John has already done some experiments with combs with really good results working in frequency space.
Okay, right. Thank you so much.
Well, I think we are really seconds away from lunch and then the beach, but I think we should thank Andrew and then just a few closing remarks. But let's thank Andrew for acting spectacular.
Thank you all. So I'm going to switch now from my role as presenter to organizer. And I just wanted to take a moment to thank a few people for this, what I thought was a wonderful conference. First of all, again, President Strupa for making all of this possible. Thank you very much. My co-organizer, Jeff. But especially the person, someone mentioned the dog that did not bark, Sherlock Holmes. The reason this conference has gone so smoothly, you got fed on time, You got your coffee. There were Danishes. Everything was good. Everything worked. I want to acknowledge Sarah Carranza. And we have a small gift for Sarah.
This is beautiful. Oh my gosh. Yeah, thank you so much. Aw. Well, nice to meet everyone. You guys all have safe flights to home. I hope you guys enjoy the conference.
Yeah, thank you. So now I'm going to turn it over to Jeff for some concluding remarks. Let's see here. Here, keep that there. I'm just going to load something up here.
Oh, okay. Go right ahead.
No questions. Where is it? Here we go.
You gonna use my computer or their computer?
Oh, no, I'll use the...
Good. Okay, I'll take this away.
Yeah. Just have a quick PowerPoint to load up in there. You were on the red shirt.
Tonight I meet some friends of mine in Los Angeles.
That one, yeah.
No. Yes.
It's in black background. You can leave it fine. It's going to play something in a second. So. I don't even know what that is.
Yeah, no, that's right. Yeah. You have to be fast in both cases. Yeah. Maybe.
I have no idea why it does that. I don't know. Just go ahead. Sit. Yeah.
Yes. Right.
Okay. Just really, literally a few seconds left. We do have several new conferences coming up, but in particular, I want to highlight this one that Daniele has been generously offering in southern Italy, and on superoscillations. This is really a lot of fun. And the next one is next summer, June 12th, arrival date the 12th through the 16th. And if you're interested, let us know. Well, that's a very nice one.
Maybe after talk we just heard by Andrew, we should call it superoscillations and beyond.
This is the third one.
This one of the number 4 will change the title.
They're fantastic. Lots of progress there and a lot of fun. And we eat.
Make sure you get notes about this. So if you want to participate, you let us know.
And the meals are all served right down here in the beautiful. It's really stunning. It's one of the most beautiful places in the world. Next, this is for Yakir's 80th birthday. We had a festschrift, and that's this right here, and a really phenomenal. It's a phenomenal book. Here, Tony Leggett made a nice one, Francois, and Shmuel made a fantastic one. And I printed, just for your enjoyment, I printed out just Shmuel's chapter, which I encourage everybody to pick up. And one other chapter, which I encourage everybody to read, and just historical note, there were only 2 times in my life where I think my life almost ended. And believe it or not, they were both by laughter. So this one was a talk given by Alex Pines about Yakir, about historical, I didn't even know what to say. But this is a print, this is a, we typed up
his talk, and it is so funny. So this is also in Yakira's 80th one. I highly recommend that. And the other time I almost died by laughter was with Yakira in a movie theater. I mean, basically suffocation. So, but the one by Alex Pines was one of the funniest things I've ever heard. Okay, so we are also going to do another one for Yakira's 90-ish birthday, and we're hoping to get, if you're interested, contact us for details, and we're hoping to get the chapters by the end of the year. So more information to follow. And finally, this is really it. We have another really exciting offering coming soon, and this is something we call the Aharon of Archive. So Daniele has generously set up kind of a big operation through the library to receive all kinds of historical material about Yakir and all kinds of historical records. And one thing in particular is for almost 35 years, since I was a first-year graduate student, there was so much that Yakir would say that I just simply didn't understand. So I just simply put down one of these video cameras and just started recording everything. So I have almost 35 years, and I think Sandu was the first one to suggest that I get this down on videotape, because there were so many things that were happening that were ingenious gems, priceless things, and then we would only end up publishing, I think some relatively small percentage of all the things there. And Bill Unruh was telling me an example in which another one of our really iconic deep thinkers of our age was, of course, John Wheeler. And Wheeler made very careful notes, apparently, throughout his life of new ideas he had. And but I think these are just sitting, or maybe, Paul, did you tell me about this, or did Bill?
Well,
the notes.
If I could just
Yeah, please.
interrupt. John Bell told me in a conversation once that he met Wheeler, who had this very disarming habit that if you disagreed with him, he'd say, just a moment, what you're saying is very important, I must write it down.
Wow. But there's a huge amounts of these. They're just collecting dust somewhere in Pennsylvania for decades now. I'm sure there are gem after gem. Anyway, so we're not going to let that happen. We've got 35 years of video that we've been working really, really hard to make them available, to transcribe them, to index them. There's enormous amounts of material in there. And one other thing, Yakir's collaborators, if there were somebody else in the room other than just me and Yakir, you'll notice I'm sending you videos, and just to remind you of research collaborations that didn't end up in papers. And the amazing thing, what I'm finding is, even if those are 30, 35 years ago, when we go back and ask Yakir, even if nothing has happened, right, that we're aware of on those research topics, Yakir is either your subconscious or your... I don't know what happens, but Yakir has spent another 30 years thinking about it, and there's huge amounts of new information that Yakir has about those topics. So those are really, really very valuable.
Jeff, I have an advice for you.
Yeah, please.
You know that Yakir and I are preparing an
Oh.
online course. Now,
Yes.
it turns out that in many places in the world, you pay a certain person, you give them the video,
Yep.
and then they transcribe it to you.
Right.
And then you can give the author to edit it. But it's such enormous.
It's enormous, yeah.
And it's cheap. We have one guy in India, in Cairo, and these people are good. The English is good, and then they transcribe everything to text, and then you have to edit it.
I did try that a little bit. And we may end up getting that. Right now, I'm just doing everything. The issue is that, in contrast to John Wheeler, all the notes and it turns out I may be the only person in the world that can read the notes but thank you, Avi. It would be good if we could do that. But at this point, with the accuracy, I'm certainly we're getting there. It'll be all.
And I want to thank Jeff, because he's the one who's taken the lead on this project. Lots of work, but I think it's going to be really fantastic to have the archive to easy access to all this trove of ideas. So thank you, Jeff.
Yeah, no, thank you. I'll just give you a couple second clip to give you an example. So much, when you guys start getting into this, when we make it available to you all, you'll find so many examples of things that are just thinking out of the box, you know, and please remember to grab Shmuel's chapter for the 80th Festschrift. But Shmuel's chapter is an incredible example of thinking out of the box, I think. Too much? Okay, no, I disagree. Usually we're taught not to do that, right? We're taught, that's the status quo, don't think too much outside the box. But let me give you one example, and this was, let's see, we just had the Wheeler, there was a Wheeler symposium, I think it was in Baltimore, mid-90s, somewhere in there.
His 90th birthday conference, so that was in Princeton.
No, Princeton. This was a Baltimore one, okay.
Well, there was an occasion when Wheeler was in Baltimore.
Well, that's where it was. And I remember as I went down with Abner Shimoni, and he had, of course, I had been studying what Lucian Hardy had been doing, but this is the first time I actually physically met him. And so I became very interested in his, his double Mach Zender, and I was struggling to try to apply weak values to it, really struggling. And then luckily for me, Sandu showed up in Tel Aviv, and as he does for, I think, all of us, recohered me, I don't know, unconfused me or something. And so this is just an example of what's working on that original Hardy example. Let's see if it'll work. There we are. So that's somewhere in the mid-90s, I think. But you see lots of this. And there were even in these interactions with Sandu, we got quite far in something that was only published like a week or so ago in PNAS, like this particle model of the weak reality. So you see there's lots of gems like that go on in time. And finally, I'm going to just, there are some other very fun things in there. As we all know, Kip Thorne made a few spectacular movies with Christopher Nolan. We got some of those in there too. And so I'm not going to play this whole thing, but here's an example of a movie. We're going to go to lunch now and then beach, but if anybody wants to sit and listen to it, this is an example of one of our movies. Let's see if I can get it. What's that? Oh yeah, that was me. If you know, being recohered by Sandu and Yakir. But here, if you want to stay and watch, it's about 5 minutes long. But if not, go to lunch. And this is a. It's a little dated, but. Can you hear okay?
The description of the particle at a given time is with two wave functions, one coming from the past and the other coming back from the future.
What the hell is going on here?
So you have two options. If you put your mother inside there and all the surroundings that you grew up in, and then you all go backwards in time, then indeed your mother will become pregnant, and you will become younger and younger, and finally go back inside your mother. But if your mother is missing, there are other parts of the surrounding is missing, then instead of this happening, you come to the point where you miss something there, and then instead of growing younger, you start to grow older again.
Great Scott! Jennifer could conceivably retire her future self. The consequences of that could be disastrous. Dad, what do you mean? I foresee two possibilities. One, coming face to face with herself 30 years older would put her into shock and she'd simply pass out. Or two, The encounter could create a time paradox, the result of which could cause a chain reaction that would unravel the very fabric of the space-time continuum and destroy the entire universe. Granted, that's a worst-case scenario. Destruction might in fact be very localized, limited to merely our own galaxy. Well, that's a relief. I sure hope we find Jennifer before she finds herself.
Up to now, all the ideas of time machines and of possibilities of the future coming back and affecting the present always led to terrible paradoxes, like I'm going back in time and I kill my grandfather. How is it possible to be alive?
He just
Okay, all right.
not seeing things.
I'm going to pause it here. If anybody wants to watch it, I don't want to delay lunch, but I'll keep it playing if you want to watch it. It's hilarious. But anyway, that is it. Thank you so much for coming. It was really fun.